Hello. Hi guys, good morning. Welcome back to a new video. In this, we're going to see Fenwick trees. Now, it is not like other videos in which you are always confused how actually the Fenwick tree is working, how it is solving my problem, what was the problem, how it is solving it, and actually how the code is replicated with the visualization of how Fenwick tree works. That's the reason in interviews you might forget the implementation of Fenwick tree because the instructor has never taught you how to think about it. So yeah, let's begin and see what is actually a Fenwick tree. Now, before even seeing what it does, all that stuff, let's firstly see where it is actually used. Maybe in future you just want to bookmark it, then you can bookmark it that okay, in all these places I can actually use my Fenwick tree. So Fenwick tree, also called as a binary indexed tree. You will get to know why this is called as a BIT, binary index tree, but it's mostly used to find range calculations. For example, range sum, range maximum query, which means in a range. Again, range sum means that in a range you have to find the sum of the elements in a range. In a range you have to find who's the maximum element in the range. In a range you have to find who's the minimum element in the range. In a range you have to do some XOR operations. Mostly range queries can be done by Fenwick trees, but the other applications which you can see are inversion counts, which are very famous interview problem which is asked in an interview. And this problem we will actually also see in the next video also, which is the application of this particular Fenwick tree. Now, we saw that Aryan, you told that okay, you can do range sum operations, but I have also heard about sparse tables, and I've also heard about prefix sums, which is the most commonly used range sum operations. And for the folks who don't know prefix sum says if you have a nums, then you will take the prefix sum, as the word itself says, prefix 2 plus 1 3, 2 plus 1 plus 3 6, 2 plus 1 plus 3 plus 4 10. So this is, I'm taking a prefix sum and then plotting it here. Because of this prefix sum, let's say if you ask me and tell Aryan what is the range sum of this j to I, then I'll say okay, I will take j minus 1, 10 minus 2 is actually the range sum for this specific range, which is nothing but 8. So Aryan, I can easily go and find the range sum using my prefix sum. Then why would I ever need something else to learn? As simple as that. And also this is again a O of 1 operation, which is most optimal time constraint which you can actually achieve. So why you need anything else? Because you would need, if I go and ask you, bro, what I will do is I will update your nums itself. After every query, I'll update your nums. Although I'll ask you, bro, what is the range sum? But then I'll go and ask, bro, do one thing, update this 3 to 4. Then what you will do? Will you go and update your entire prefix sum again? Which means you will have to go and update the entire prefix sum again. So okay, 2, 3, now it has become a 4, so you will just say it's actually a 7. So your entire prefix sum is updated, which means on every small element, one element update, I have to apply again a O of n operation to update the entire prefix sum. How is this even useful? Like you're using an O of n operation to apply the prefix sum again. So for that, people thought of okay, I have to apply on the entire range again. Rather, can I bifurcate the range? Which means can I like have a division in the range? So earlier, rather than having the entire prefix sum, I will just break it down. Okay, I will have a prefix sum of 3 elements and then prefix sum of other 2 elements. So you will see if I just plot my existing elements prefix sum, so 2 plus 1 and 2 plus 1 plus 3, 2 plus 1 and 2 plus 1 plus 3. Then, although earlier I was just going ahead, but now I have broke it down. Okay, 4 plus 5, 9. So you saw that I broke my prefix sum array itself. Aryan, why is it useful? It is useful because earlier when you were updating this 3 to a 4, then you would have to update the entire prefix sum array. But now you know it is broken at this point and you updated this specific element, so you only have to update this specific prefix sum array. That's it. So I'll only update this specific prefix sum array. I will not touch this later part. So what will happen? It will become a 2, 3 and 7. Now same way, if I go and ask you, bro, what is the range sum for this portion? You will go and ask, what's the range sum in this portion? What's the range sum in this portion and what is the range sum in this portion? Same way for the updated one, what is the range sum in this portion versus what's the range sum in this portion. Range sum in this portion is 4 minus 0. Range sum in this portion is 7 minus 2. So ultimately my range sum will become actually 9. So that is the actual backbone idea of my Fenwick tree. That I wanted something like of a prefix sum, but I cannot afford to keep on updating the entire array again and again. So what I will do is I will break this entire array down into some segments. Again, the actual idea, Aryan, okay, now I got it. Okay, I will break these segments, and because of breaking, I might optimize my time. But how much? That I'm not sure of. So that is a one question which I will think of. But meanwhile, can you tell me how I will actually break it? Because breaking, how you will break will define how optimization you can have it in the time complexity of the specific range sum which you will get. So now my thought of, okay, breaking is a very standard phenomena, and we have seen many such videos of people breaking in half, and then whatsoever is remaining, then we again break in half, then again break in half. Why people always keep on breaking in half? Because half is actually nothing but a base 2 operation. So if I just break anything in half, I know for sure that ultimately I will require log into the base 2 number of operations, and that is I reduce my complexity from O of n to O of log n to the base 2. Oh, so what I can do is I can actually make my ranges as half. Like I can just try to break my ranges in a half, or basically in a power of 2. But Aryan, that seems fine, but still it is not understandable that how you actually make. Okay, let's say if this was your actual input array, and if I ask you what's the range sum of this specific portion, how will you find it? That's a good portion. So which means I'll go very basic. Okay, what if you asked me only first, again let's take another color, but what if you asked me this one element sum? So okay, which means that I should be having one element as a sum. So what I will do is I will keep one element as a sum track. Okay, one element sum I'll keep track. Now what if, Aryan, you asked me these two elements sum? And I was saying to you that I will keep my sums in a power of 2, which means I'll just try to replicate my log n kind of complexity. So I need to break my sums in a power of 2. So yeah, it is good to know that I will just get this as, because I know it is 2 elements, so I'll get it as one sum. Okay, 2 I'll get it as one sum. But Aryan, what if, okay, this you got, this 2 you got, but what about if you want to get this? Oh, if you want to get this, then you have your 2 sums. If you have your 2 element sum, you have your 1 element sum, you can just simply subtract to get just this specific element sum. Aryan, it is just 1 element. Why can't you take from the input array itself? That is obvious question, but hold on. Keep on going. You will see why I'm not taking it, why I'm taking specific sums for them. Okay, that seems great, Aryan. Now, Aryan, what about if you want to get these 3 sums? Oh, if you want to get these 3 sums, I know one thing for sure. I have these 2 sums for sure. So let's take this one sum also. Okay, for this one sum, I made this one sum and taken that out with me. Okay, Aryan, great. If you want to take these 4 sums, Aryan, 4 sums, which is a power of 2. So grab them as one sum. Okay, 4 sum I have grabbed. So this highlighted ones are the ones which I am keeping track of, so as to find any possible range sums. And that is how I'm trying to build my prefix sums. Kind of, you can just imagine that, okay, this will store the sum of the 4 elements. How I know I want to show the sum of 4 elements? Because I know I will store the sums in a power of 2. Okay, great. Now, Aryan, again, can we please go ahead? Which means, let's say if I go and ask you if I want to take this specific sum, it's 2. So it's 2. So are we saying that it is 2? It is 2. So are we saying that we have to also keep track of these 2 sums? I'll say no. Why? Because you want these 2 as sums, right? So what I can do is I have these 4 as sums. I have these 2 as sums. I have these 4 as sums. I have these 2 as sums. Then I can just subtract them and simply get this. Oh, great. So basically, I am just keeping track of just one sum here. Okay, one sum here, 2 sum here, 4 sum here. Again, I'll just keep track of one sum here, not two sums. Again, I'll keep track of two sums here, and that is how I'm trying to keep track of some range sum. Again, range is nothing but a power of 2, and I'm only keeping track of those specific sums which are actually useful for me. If it is now, how to know if it is not useful? If I can just derive that specific range sum value from some other values, then it is not useful for me. For example, as I showed you, for these two range sums, I can derive it from this specific range sum, which is 4 sums, which I have taken. I will subtract it minus 2 sums. So I'll simply get this specific, these 2 sums value. So now you have got a rough idea of how this Fenwick tree logic is actually built on backend, which means it tries to get the range sums in a power of 2, and those specific range sums are only and only, again, it is actually just a sufficient number of range sums that is required for you to get any specific range sum value. Let's say if I ask you, you want to get this specific sum. Again, you will see that it has no intersection at all. So what I can simply do is, I will get this sum, I'll get this sum. This sum you can simply see I have already stored out as one sum. This sum I have not stored it anywhere. So what I will go is, I know one thing for sure. I have this 4 sum values. This is 4 sum values. I'll subtract the 2 sums from it. I'll subtract the 1 sum from it. And ultimately, I'll get the just last remaining sum. So that is how I'm actually keeping track of only the most sufficient values, range sum values. Now, coming on back, that is the basic crux of how actually you will use a Fenwick tree to find any possible sums. But Aryan, please let us know how you will make this sums, because it seems very optimal, but how you are making it, let us know that, right? Okay, no worries. We will use a simple formula or simple funda that I can easily derive every possible values. So if you look back very carefully in this, you will see one very basic pattern that, okay, I was keeping track of one sum, just one sum. First time, I was skipping that. Next time, I was keeping track again for the first time, like again for next time, again skipping that, again keeping track, again skipping that, again keeping track. Oh, so one sum, I am doing something like this, okay? Keeping this one sum, skipping that, one sum, skipping that, one sum, skipping that, one sum, skipping that, one sum, skipping that. That is how again, you can easily see that's the entire diagram of the 16 values which you have. Or you can say 15 values for you to actually visualize. So as you can easily see, I am keeping track of one sums alternatively, and I can easily infer from this above diagram also. Again, just only keep track of those sums which you actually need, and I have derived, like I have shown above, that what you actually would be needing. Now, okay, one sums I have done and I have plotted. Again, let's imagine this sum as a bit array. Let's imagine this sum as a bit array, which I can use to find out any range sum values. And I'm trying to build this bit array itself. Okay, Aryan, one sum is done. Now, next comes is 2 sums, because I know that I have to break my array into a power of 2s. So I need to actually build it in a power of 2s also. So 2 raised to power 0 sum range is done. 2 raised to power 1 sum range will now come in picture. And again, if you go back and see that, you will see, okay, first 2 sums was actually here, then you skipped it, then you skipped, like next 2 sums were actually here. Okay, so similarly, I am just trying to plot just 2 sums value. Okay, for 2 sums, how I can simply grab these 2 sums. Again, don't go linearly back to make the sum itself. We will again use some funda. Again, this is a logical way to understand this. I will tell you in the code also how the code is actually implemented for that, but understand this logical way right now. Now, I'll simply go and ask, bro, I want the 2 sum range for me, for this me. I want the 2 sum range, which means I want that these 2 sum, I want the sum for them. So I'll simply grab 2. I'll add that with my previous value. I'll simply, again, Aryan, why you are adding the previous value right here? You can also add the previous value right here. Yeah, makes sense, but you will understand why I'm adding this specific value and not this value. Again, both are same. You might argue with me. Yeah, you are correct. But still, I'm using my already computed bit to find my new answer. So I'm adding my 2, I'm adding my 5, and I'm getting my 7. Okay, great. I'm okay. Understanding, you still argue that why I have not taken this specific 5. No worries. Hold on. Just hold on up till the length increases. You'll get to know that part. Now, same way, I have computed this specific 2 sums. if you have seen and remembered, I have skipped the next two sums and then I went on to again two sums, right? Okay, same way, I'll skip the next two sums, I'll go on to the next two sums. As I was skipping one element, here I'm skipping, I was taking one element, I was skipping one element, here I'm taking two elements, I'm skipping two elements, then I'm again going on to this specific two sums. Current element is 20, previous sum which I have got is 5, sum is 25. Again, you can easily see that I have stored this bit sum is storing, this specific bit array is storing this 25 is this 2 sum value. Okay, great Aryan. Again, skip 2, go on to next 2. Again, 3 plus 2, 5 is the sum. Okay, skip 2, next 2, 15 minus 2, 13. So that is how you can actually build your 2 sum bit array. Okay, 2 sum bit array, one sum is done, two sum is done. Next sum is 4 sum, again in a power of 2. Okay, for 4 sum, again simply for 4 sum you will keep track of the 4 element, you will skip the next 4 element, again you will keep track of the next 4 element sum. Now for this 4 element sum, you will again for the 4 element sum, you now will understand that if you would have chosen the nums to find your sum for the 4 elements, then to find this sum, you would have gone to all the 4 elements and then got the sum, right? Okay, no worries. What I will do is, I know current element is minus 3, I have computed this 2 sum value which is 7, I computed this 1 sum value which is 9. So minus 3 plus 9 plus 7 will give me 13. I have got this 13 value. Same way, I'll skip the next 4. Again, just understand that I'm actually building my these. I'll also, while showing you the code, I'll also again dry run of how the values are computed. But just hold on and understand that, okay, I'm just computing the 4 sum values. Again, skipping the next 4 sums, getting the next 4 sum value. That, okay, 0 minus 4 and plus 5. But Aryan, what's the use case? Because you will go on to just the log n number of times backwards, which means it's a power 2, it's a power 1. So powers can be just log n if the specific value is n. If right now you are currently finding the answer for a range of size 2 raised power n, which is 2 raised power 2, then you will just go on backwards how many times? Just log n times. If the specific value is n, then you will just go backwards log n times. That is how actually it is useful, that you are not going backwards n times, you are going backwards just log n times. Now again, here we are building it forward, but we will reverse engineer. Sorry, we are reverse engineering right now, but we will build it forward, going forward, build forward. Cool. Now coming on back, we'll skip next 4. Okay, no worries. Now we have built our 4 sums also. Right now, let's for the simplicity, let's build the 8 sums also. Okay, for building the 8 sum, I know, okay, minus 7 plus 10 plus 25 plus 13 will be the specific value, which is 41. And again, I can skip the next state value and again do a range sum of next state values. So now you can see I am just building my range sum in a power of 2. Now when this is done, now comes the actual part, that how I can query any range sum in the shortest possible time. For example, if I go and ask you, bro, I am giving you a query, can you please find the range sum of 1 to 7. 1 to 7 is the range. Again, I have taken a very simple range for you to understand, for you to make you understand how actually the range sum will work. I'll go and ask you, bro, can you please find this value? So you know, okay, Aryan, you are asking for 1 to 7. This is the range. Now I have computed this specific range sum values, right? It is computed for me already, and it is being stored at this specific locations. So what I will do is, again, this is the natural, this is the normal array. But the bit array corresponding to that I have already made above. If you have known, I have already made this bit array. Bit array is already made above. Now when this array is made for me, I know one thing. One sum, again, I want the from 1 to 7, I want this range element. So what I will do is, I will get this specific sum, one sum. I'll get the next 2 sum value, which is this specific value. I'll get the next 4 value, which is this specific value. And with this just 3 values, I have got the range sum of 7 elements. And that is how your query is useful. Now, how it will look like? Simply, again, I'm just showing you the code, but I will explain that code also. So the code is very, very short and simple. That's the reason I don't prefer segment trees over Fenwick trees, because in an interview, it will be very highly unlikely that you will be implementing a segment tree, because it's a very long code. Because segment tree itself not great until unless you apply lazy propagation. And if you add lazy propagation in a segment tree, it becomes very big code. For the folks who don't know what all that stuff, just forget that part. So that's the reason I always recommend using a Fenwick tree. Very short and simple 3-4 liner code. So if you want to query, I will go and ask again, Aryan, you have only passed in one argument. Aryan, you have only passed in one argument, which is ID. What does ID means? I was about to calculate the range sum. No. Oh, this ID means that you will find the range sum in the range of 1 to that specific ID. Okay. But Aryan, don't we have a liberty to find the range sum of L to R? Are we always finding the range sum from 1 to R? Bro, if you want to find the range sum from L to R, just go and find the range sum from 1 to R. Just go and find the range sum from 1 to n minus 1. And then subtract that. Simply get the answer. Simply get the answer. How it is such a big deal? No, right? That's the reason. I'll find the range sum from 1 to ID. How I will do that? I will use this kind of formula. Again, it's the shortest possible formula written. I will expand that and tell you. But for you to understand, please understand some basic concept of bit manipulation. ID is simply, again, ID is simply a number, integer. But to explain that, I will convert that to a binary form. Minus ID is again a negative integer of same ID. But then how, again, as I spoke earlier, I will convert my ID to a binary form. How a minus ID is converted to its binary form? By using its 2's complement. By using its 2's complement. How it is done? Simply flip these bits, flip the natural bits which you had, and then add a 1. You will get a 2's complement, and that is how you represent a negative of a number, right? 2's complement, say simply flip the bits of the original number, which is positive numbers, add a 1, you will get a 2's complement, and that is nothing but a minus of that specific ID. That is the basics of bit manipulation which I am teaching you right now. Now, AND operation is nothing but ANDing these two binary numbers which I have got, and then minus is nothing but whatsoever you have got by doing a AND, subtract that from the original value. Again, it's a normal subtraction operation. So this operation is entirely which this line is doing. That's the reason. It's so short and simple. Although it might seem complex IDMIs, but no worries, you'll understand that. But in Crux, what it does is it removes the last set bit. I'll make you sure that you understand that part. But you're simply adding the current. Now what will happen with this is, you will see that you were at, again, I asked you to find the range sum of 7. 7 in the binary form is 1, 1, 1. So as you saw that you will add this value, right? You will add this value, you will add this value. Again, you will add these values from your bit array, not the natural array, because in bit array you would have computed the sum, but right now I'm showing it from the natural array for the reference. So what this operation will do is, again, don't go into very deep. I'm just showing you in deep. I will let you go. I will take you deep, not that deep, but yeah, I'll take you deep. What will happen in this is you are adding, again, ID is initially number 7, binary form number 7. So you will add that in your answer. You added this specific value in your answer. Okay, added that value. Now this operation will remove the last set bit. Your 1 is gone. You will get a 110. Okay, 110 is this specific number. So you will add this specific value. This specific value I have added in my answer. Added next value. Again, value will keep on going until my ID is not equal to 0. Now you will again ID, again this operation right here will remove the last set bit. Last set bit is this specific one. It is removed. You will get to a 100. Again, add this specific value, which is this specific value added. Now, when this is done, you have added the value. ID, remove the last set bit. Last set bit is removed. It becomes a 000. 0, which means breakout. So you have added these 3 values in your answer, and that's how you actually perform your query operation. Now, when you have understood this, let's quickly go and understand deep by deep how in the binary form, which is dry run, this specific example itself. Query was 7. Query was a 011. I simply asked, bro, can you please query for 7? If you remembered in the loop itself, I just firstly added the bit value for that specific ID. Bit value for that ID, if you had remembered, again, bit values are above. Take a snapshot of this for your reference. Bit value is above. So this is the bit value, which is 10. Again, this is the bit array. For your reference, I have made the bit array, but I will keep the reference of the original array for you to show how original array, from that original array I'm just getting the answer. Okay, from the bit array I have got a value as 10, which was value as 10, right? Okay, I'll just get that value 10 and add my n in my answer. Now I have to apply this operation, which was this, and I know this operation removes the last set bit. How this operation works is that you have your ID, which was the binary form of number 7, then you have to apply this operation. How this operation will work is ID was a 0 1 1, minus of ID will be 0 1 1. If I flip the bits, it will become a 1 0 0, right? 1 0 0. If you remembered, I told you flip the bits and add a 1, flip the bits, add a 1, so it will become a 1 0 0 1. By adding a 1, it becomes a 1 0 0 1. Now when you have this and this, simply do a AND operation between them. After doing an AND operation, I have got this specific value, which is 0 0 0 1. This is the AND value, this is the AND value. Now when you have got this value, simply subtract this AND value from the original ID. Original ID was 0 1 1. Remember that fact. Again, remember it, or maybe dry run with me, which means take a pen and paper with me. Now subtracting a 0 1 1, which is the above value, you will get a simply 0 1 1 0, and that is, you can see visually, you can see you have removed the last set bit, or basically flipped the last set bit. Flipping as in removing the set bit will become unset, and that's how you actually perform this operation. So what you will do is, you have got your ID, new ID as 6. Again, when your new ID is 6, go and ask your bit array. Your bit array will give you this specific value, which is 25, which is the range sum of these two values. Again, add in your answer 25, and simply again now remove the last set bit. Apply the exact same operation. Apply the exact same operation. Your ID will become a 4 now. Okay, go and ask for this value, which is 4. If I go and ask back, my 4 value was actually nothing but a, this was 25, this was a 1 minus 3 plus 9 plus 7. This is not a 1, this is something else. Let's see, it is 13. It is 13. So I simply add a 13 for that value. So I'll go and add a 13 for that value, and I again go and remove the last set bit. It will become a 0. As it becomes 0, simply break down, and that's how you know that you added this value. Again, you added this range, and this range, and for these ranges I have got this value from my bit, this value from my bit, this value from my bit, which stored the value for that specific ranges, and that's how you can simply solve it. So your answer, which means query for 7, it became a bit of 7, bit of 6, and bit of 4 values, which was range of 7,7, range of 5,6, both are inclusive, and range of 1,4. And that's how you have got the range values. Again, this, you know, a number will have just log n bits, so I'll for sure will break down into log n, at max log n number of ranges. So that's how I know the time complexity for this operation. Again, we know that we have at max log n number of bits for that specific number. That's the for sure the loop, because see, it is nothing but a loop. It is nothing but, if you go back, it is nothing but a loop, ID, while loop, which actually removes the last set bit. And I'm saying a number can have at max log n bits. So at max you can remove log n bits from this number n, and that's how you know one thing for sure, that you will apply this operation log n times to find any possible range sum, and that's how you can simply solve it. So that is a simple thing which you can do. Now the code will look something like exactly same as what we have seen above. This is the exact same code of query, but Aryan, this is a code for query, which means this code can only be applied after I have built my bit array. How you will build the bit array itself, let me know, let us know that also, right? No worries. The actual, if you want to build your bit array itself, again the code for this is exactly same, right? For the query, for the range query. But to build the bit array itself, I'll simply use the reverse code, which means if you look back this code, you had your ID, you was removing those elements and adding that in your answer. Now I will use a reverse funda. I will, from the number, I will keep on adding that. As you will see, it is ID minus equal to, again, this is, I am telling you the funda to remember that for your interview, but I'll actually derive and dry run that also. But for now, let's understand, because see, everything in coding is not about understanding. If you forget this specific one line of code, you are done. You will end up writing 5 lines of code, which will waste your time in an interview. That's the reason. People will say, don't learn in coding. It's not about learning in coding. DSU, you still know, like you still have learned a part of it, right? That's the reason. Remember this so that you are fast in it. So what I will do is exactly same. As you saw that I'm simply adding my answer, the bit value. I'll simply, in my bit value, I'll simply add the value itself because I'm updating it. As you can see, update it. This simply says update the index with that specific value. I'll tell you what that means, but right now it says operation is update that specific index with that specific value. So until, because I am starting and going on updating, so until it reaches the n. Again, you just remember that it is simply a reverse of the query. Query is you are simply reducing your I, and update is you are simply increasing your I. If you increase something, then you will simply make sure that it is reaching n. If it is reaches beyond n, you will simply stop. That is the funda I told you for learning this specific piece of code. Now I will make you understand how it is actually working. So if you had gone and remembered, if I go and ask you, you have to build the specific bit array. Now, first time you encountered the element 5, you know that at what all places my 5 will have a contribution. If you have remembered, I wanted some specific range sums. If you remembered, I wanted the range sum of 1 element. I wanted the range sum of 2 elements. I wanted the range sum of 4 elements. I wanted the range sum of 8 elements. So you can see this 5 is contributing in the range sum of 1 element, 2 element, 4 element, and 5, and this 8 elements. So I'll do the same thing. I know that this specific 5, again, remember this pink 5. This 5 is nothing but its bit value, but remember this pink 5. I'm showing you how this pink 5, where all places he will go. This pink 5, he knows he has to go on to one range sum. Okay, one range sum he has gone. Range sum for 2 values, he has also gone there. Range sum for 4 values, he has also gone there itself. And range sum for 8 values, he has also gone here itself. Oh, great, Aryan, great. But Aryan, what this goes means, you can see that, let me just iterate one more, then I'll show you. So now for this specific 2, if you remember that this 2 also will go some places. It will go in this 2 range sum, it will be included in this 4 range sum, it will be included in this 8 range sum. Makes sense? So what happened? This 2 went on to this 2 range sum. This 2 went on to next 4 range sum. This 2 went on to 8 range sum. Oh, great. So you saw that this specific bit value will be 5. This specific bit value will be 5 plus 2. So I am doing one thing. I know the indexes. Again, to make one thing for sure, that binary index tree have indexes from 1. Indexes from 1. Just write it down anywhere in your entire room. But remember this fact. Bit is always from index 1. If not, then make it index 1. So I know that index 1, I will have a value 5. But I know, okay, his value is 5. But at what all places I can give his sum. So his sum will go at this one index, 2, 4, 8. These all places his contribution will go, which means he will be added. That is the reason the code looks like that. You have the value id 1, index 1, you have the value 5. So your 5 will be added that bit of 1, then the bit value will become your id value will become a 2. So at the bit of 2, again the 5 will be added, same value 5 will be added. At the bit of 4, again the value 5 will be added. At the bit of 8, again the 5 value will be added. And that is how your actual loop works and populate your bit values. Cool. So same way, a dry run, simple dry run, that now you have your 9. You know that you will simply propagate that 9 forward. This value, this value, this value, and so on and so forth. So that's how your every element nums of values is propagating to your actually bit values, like in the bit, and just propagating that in the powers of 2. Like just simply add a 1, add a 1, add a 1, and simply keep on going. Now how the actual code will look like, exactly same as I've showed you. That how the dry run will look like is that if you want and have a specific id, apply the same operations. Do a minus id, minus, which means complement of this number is 1100. Add a 1, you will get a 2's complement, which is 1101. after doing it, do a AND operation with ID and minus ID. You will get a 0, 0, 0, 1. Then do a plus operation. Doing a plus operation, I will simply get the next as 1. So you saw that I had earlier 1, 1. Then after doing the operation, which is ID plus is equals to ID and minus ID, I have got this specific bit as 1. Thus, I'll simply know that at this specific ID, I need to update the 9's influence. Now, everything, dry runs, all the stuff is done. Let's quickly see that what we have learned. We have learned that we can find the range sum in any range L to R. Aryan, but you showed the update from 1 to R. I've showed you that I have shown update from 1 to ID. But you can bifurcate that always from 1 to R minus 1 to L minus 1. Right? And we have seen that we can do a point update. Aryan, this is you never showed. Bro, the entire code is a update code, right? You just have a specific ID. You have a specific ID, let's say 1. If I want and say that, okay, at index 1, I add some value 2. So at next 1, rather than 5, I want to add a value 2. So I added a value 5 plus 2, it becomes a 7. So now I will simply propagate that values, which means the plus 2 which I have added, I simply propagate that to all the bit values also. One quick fact people get confused in this is that, Aryan, that seems okay, but I cannot modify this code according to the demand of the problem. Right now, you updated the value, which means you added something in your existing value, right? But what about the problem is saying me that you modify this, which means instead of 5, put a 7. How about I will do it? Now, one group of people will come and say, hey bro, find the difference and do it. I'll say do one thing. You have to make the contribution of this 5, because see, you are removing this 5, so you have to make the contribution of this 5 as 0, like as nothing, right? Do one thing. You have already made this update. Now to revert the contribution of 5, just simply apply the same operation by saying at the ID of 1, apply minus 5 as the update value. So what will happen? The contribution of 5 will go away. And now when this contribution of 5 has gone away, now do the actual update, which is value of 7. That's how you can actually use the same piece of code to modify stuff. If I ask you, just update the value. Okay, it was a 5, update with the value plus 2, like add a plus 2 or subtract a minus 2 or subtract a plus 2, which means or do a minus 2. Then you will simply do okay plus 2, because you can simply see how it is impacting. It is adding in your existing bit values. So whatsoever you are bringing in, it is simply adding in the existing bit values, right? So that's how you can actually modify this simple piece of code to meet your own demands. Now so we have seen that we can do these operations. Now the code is exactly simple, exactly same. Again, keep this code as a snippet with you, or you can just make sure that you can actually write this code very fast, because it's very simple code. Firstly, I will initialize my n, right? Why is this n needed? Because you know that you need to go up till the limit of n. Now Aryan, what is this n? N is the size of your array, for which you have to make the bit array itself. So if you have remembered, our main function will look like that. I will make a bit array. I'll make, again, this bit array is also global. I'll make this bit array with the size of n plus 1. Aryan, why n plus 1? Because I told you your array is 1 indexed. If your array is 1 indexed, you will have n plus 1 indexes. So I will make my bit array also 1 indexed. Again, here I have put in my a array also 1 indexed, but your a array can be a 0 index. If it is a 0 index, make sure you populate the correct bit array. Your update will always be 1 based. Your bit indexed is always 1 based. Make sure that part, write it down, else you will get things wrong, very wrong. So your I will be from the 1 itself, and I'm updating I'm just updating my entire, I'm just in the very beginning, I am inputting my elements of nums, and I'm trying to build my Fenwick tree, which means contribution of every element. In the if you remembered, the index 1 I have 5, index 2 I have next values and stuff. So I'm just simply updating my bit array because of this update function every time. And this will make my entire Fenwick tree for me. Now, I can simply go and ask for the queries. My query will look like, again, the actual essence of Fenwick tree is when you are updating the nums array. If you're not updating it, you are only querying it, which means you are only asking for a range, then always apply prefix sums. It is much more efficient. But if you have to update something, then please go and apply your Fenwick tree. Great. So now type 1 query is, please go and find the sum in the range L to R. Please go and find the sum in the range L to R. When you have to go and find a sum in the range, go, as I have told you, go and ask for query of R minus query of L minus 1, because you remembered query will give you from 1 to R. Query will give you from 1 to L minus 1, and you have to go and find for L to R and simply get the answer. And if you want to do a replace function, again, it's a replace function they have given, which means replace the index value to some new value. So I told you, if you have to replace some value, first simply remove the existing of the existing value. So existing value was minus of existing value was a of id. I removed its existence by doing a minus of aid, and then I updated its existence with the a of id. Okay, that is how I can do it. It's a new value. It's a new value which I have got, and as you can see, I have updated a new value also. It's a new value. Now the main functions of query and update will look exactly same. The update will simply go and the exact same function, update up till id less than equal to n. Query is also exactly same, get the answer. Exactly same as what we have seen. Now for the complexity part, we have seen that each update function will go on to log n hops. So each update will take log n steps, and in the very beginning, if you have seen, I am doing update for all the n operations. So for sure n log n will be for sure there as the time complexity to actually build your bit array. For every query command, I will use a log n time, because I know I can still have log n hops backwards. So it will be q log n for the q queries which I have. Space is again O of n, because I'm just building a bit array of size n plus 1. That's it. And that's how you can actually use your Fenwick tree. Now, there is a question which is a hard question, but it is a very, very easy questions which you can do as a practice after watching this video. And its actual implementation, like its entire code, we will bring on in the next video, which is a part of our 100 days 100k placement challenge, right? In which we discuss the famously asked questions. And right now we have just seen point update and point query. Sorry, we have seen point update and range query. Right, we still, because of simple code of Fenwick tree, we still can use a range update and point query, which also your segment tree can do. But range update and point query, which also your segment tree can do, but then you would need your lazy propagation. Range update and range query, again segment tree, lazy propagation. So for these two, we have to use segment tree for lazy propagation, but because of Fenwick tree, we can also make its code very short and simple. Although its code, because in this you have to use 2 Fenwick trees, it might look complex, but it is much easier than that of your lazy propagation. It is also very easy, a very slight modification in your existing code and you will get it. Again, if the video not comes in and if you still want to learn these 2 remaining ones, then just go on to cpalgorithms.com. Just write on Google CP algorithms. You will get a website page. In that, search for Fenwick tree. You will get these 2 variations also. Don't study from anywhere else. Everywhere else, it's such a bullshit and such a crap code. The piece of code is so beautiful there. Cool. That's it from me. Thank you for watching. See you. Goodbye. Take care. Bye bye. That's a long video. Bye bye.